Good evening, everyone, and welcome back to another Our Universe Revealed, which is the public lecture series from the Department of Physics at the University of Notre Dame. I'm Jonathan Crass, the coordinator for the series, and I'd like to extend a warm welcome to you this evening and thank you all very much for joining us. You can find out more about the series and our upcoming events at our website. That is at nduniverse.org. You can also find us on Facebook and YouTube as well. Tonight, we're going to be following the usual format of our online events with a presentation followed by questions. You can submit those questions either as we go along or at the end of the talk. If you're watching via Zoom, you can do this via the Q&A button at the bottom of your screen, or if you're watching in YouTube, you can use the chat feature on the right-hand side of the screen. And if you're on either platform, you can use the link to the Google form for questions that I will send out shortly. Tonight, it is my pleasure to welcome Dr. Erika Holmbeck to Our Universe Revealed. Erika did her undergraduate degree in astrophysics at the University of California, Los Angeles, before coming to Notre Dame as a graduate student in 2015. She recently received her Ph.D. from the Department of Physics at Notre Dame and will be moving to a new position as a postdoctoral researcher at the Rochester Institute of Technology in New York over the summer, and she'll be working with Richard O'Shaughnessy. Her research focuses on studying the processes and environments in the universe where it's possible to create the elements we see around us on planet Earth and elsewhere in the universe. And tonight, she's going to give us a little bit of an insight into some of that research, her cutting-edge results. So welcome, Erika. Thank you much for offering to speak to us this evening. And let's see if we can get our screen sharing working and see your slides.
Yes, here we go. You can see this, right?
That looks great to me. Over to you.
Great, perfect. Well, thank you so much for the introduction and thank you for the invitation to give this talk. Thank you everyone else for tuning in to hear about my research. I hope that this alleviates some of your boredom in this time, and I hope it doesn't do the opposite. I really hope you don't snooze through this. I think it's really interesting, and I've titled my talk Cosmic Alchemy because, as Jonathan said, what I study is how the universe made the heaviest elements like gold out of lighter elements, things like hydrogen and iron. Okay, so let's start with the periodic table of elements, which I hope many of you have seen before. We can find almost all of these elements here on Earth. Of course, some of them are man-made, but most of them we find naturally. And if you've heard this quote by Carl Sagan, "We are made of star stuff," he basically means that these elements are made by the universe. The elements that go into our bones, our DNA, they were made in the universe, mostly through the lives and deaths of stars. Now, in the physics department at Notre Dame, a lot of us are involved in a field called nuclear astrophysics, and it sounds like a mouthful, but basically we investigate where these elements come from. So when Carl Sagan said star stuff, what exactly does he mean by that? And that's what the field of nuclear astrophysics is dedicated to understanding. So let's start at the beginning. This plot, I will step through it in a few slides, but this plot shows the abundance of elements that we observe in the solar system. And just notice as I step through this plot that it is on a log scale, which means that, for example, hydrogen is 10 times more abundant than helium, and it is more than 1 billion times more abundant than some heavier elements that we'll see. So these lightest elements, hydrogen and helium, a lot of that abundance was made by the Big Bang almost 14 billion years ago. Big Bang nucleosynthesis was responsible for creating hydrogen, helium, and just a little bit of lithium. We can also have helium production from stars. So for example, our sun is currently undergoing a fusion process where it's basically converting 4 hydrogen atoms into 1 helium atom for all of the hydrogen, most of the hydrogen in its core. That's happening in the sun right now. Later in the sun's life, it will continue this fusion process and turn those helium atoms into carbon and oxygen, but really nothing more than that. The sun just kind of fizzles out after that. Heavier elements, the fusion of heavier elements beyond carbon and oxygen are reserved for the most massive stars. So the most massive stars can have many different types of fusion processes. I've listed just a handful here, but there are many, many types. And these very massive stars can create elements up to about iron and nickel. So elements like neon and magnesium, silicon, sulfur, all the way up to about iron. After iron, stars can no longer make elements through fusion. And I think we might all know that at that point, these massive stars undergo supernova and they just kind of stop there. So the most abundant natural elements that we find here on Earth, elements like helium, carbon, oxygen, and iron, these can mostly be accounted for by fusion in stars and then their subsequent stellar deaths. But that leaves a lot of the periodic table unexplained. There are all of these other elements that we find here on Earth, elements like silver and gold and platinum. We can mine these on Earth, but these elements cannot be made through fusion processes. They require a different type of process entirely. And that process is something called neutron capture. Now, the way neutron capture works is if we just have some toy nucleus that has Z neutrons and N protons in a neutron capture process, a free neutron will come in and be captured by that nucleus. So now that nucleus just has one more neutron. This should make sense. But that nucleus might be unstable. And what happens is that neutron can convert itself into a proton through a process called beta decay. And when it converts into a proton, that nucleus has now completely changed identity. It's now a different element than it was before, just through this neutron capture and subsequent beta decay process. The easiest way to visualize neutron capture is through something called the chart of nuclides. This is basically the periodic table for nuclear physicists. The way you would read this is the element on the y-axis increasing, so hydrogen is all the way in this lower corner. And on the x-axis is the number of neutrons in an isotope. So every row on this chart shows the isotopes that can exist for each element. And for some elements, it's a lot of isotopes. And when we look at the elements in this way, we see that there's more than just 120 something known elements. There are actually over 3,000 known isotopes of those elements. On this chart, only the black squares are stable isotopes. It's only a couple hundred. Everything else on this chart, all of these colored boxes, represent unstable isotopes. The farther you get from what we call this valley of stability, the shorter lived these isotopes are. So if you make an isotope here, it will decay into something very quickly. But that's not the whole story. There are many other isotopes that could theoretically exist. These gray regions show the theoretical extent of isotopes that, again, could exist. We just haven't been able to measure any of these because, again, they live so short, such a short amount of time that in order to measure them in a lab like at Notre Dame, we would have to create and detect them within milliseconds or microseconds. They live for a very short period of time. And on this chart, everything to the left of this valley of stability, we refer to as proton rich, just because proton number is increasing this way. And on the right of this valley of stability, all of these isotopes we call neutron rich. This is the neutron rich side of stability. So when it comes to neutron capture, the neutron capture process will involve these neutron rich nuclei. Okay, so let's just zoom in on a random portion of this chart to see how neutron capture occurs along this chart. So I'm just zooming in. And I picked a random nucleus. I picked neodymium-146 for no reason. Say that this nucleus undergoes neutron capture. So first it will capture that neutron, and in doing so, moves to the right on this nuclear chart. Remember, each row is the same element, and as you go to the right, you're just gaining more neutrons, you're going to a different isotope. So this isotope, it's still neodymium, it's just a little bit heavier, it has one more neutron. But this isotope, I can see here, it decays in about 11 days. So after about 11 days, that neodymium, that extra neutron, will convert into a proton. And on this nuclear chart, it moves up and to the left. And when it converts to a proton, it becomes that next element on the periodic table, which in this case is promethium. So this is essentially how we can visualize neutron capture on this chart of nuclides, just with this stepping to the right and then stepping up and to the left with neutron capture and beta decay. All right, with that being said, there are two main types of neutron capture processes. There's a slow and a rapid neutron capture process. We abbreviate those with S and R process respectively because it's much less of a mouthful. In an S process, neutrons are captured slowly. There's not a lot of neutrons are involved in the S process. And because of that, this S process involves nuclei that are stable. These stable nuclei, again, the black boxes, they just patiently wait for a free neutron to fly in from somewhere, and then they can capture that and beta decay to the next nucleus. On the other hand, the R process involves nuclei that are extremely neutron rich, and the R process happens when you have many of these free neutrons available. So what happens is those nuclei are pushed so far from the valley of stability in this neutron rich region before those unstable nuclei have a chance to undergo beta decay. So the R process takes place very far from stability. If we go back to our toy nucleus again with just Z neutrons or Z protons and N neutrons, and our process would look something like this, where it captures all of these neutrons before one of them finally has a chance to beta decay. So the S and the R process essentially accomplish the same thing. They both undergo this series of neutron captures and beta decays to make heavier elements. But as I said in the previous slide, the R process and the S process differ in the amount of neutrons that are involved. So neutrons, free neutrons, are unstable particles. They only live for 10 to 15 minutes. In an S process, you only get one of those every now and then. But in an R process, you have to have many of those at one time. So again, an R process involves high neutron flux. It involves very unstable nuclei, while the S process involves just a couple of neutrons every now and then and just occurs along those stable isotopes on that nuclear chart. Okay, so at this point, I think you're all R process experts and you're ready to visualize this for a whole set of nuclei. This is, again, that nuclear chart. Remember, the black boxes are the stable isotopes. And this movie that I will play in a second is a simulation showing how the R process occurs along this nuclear chart. So instead of just one marching along, I'm going to show a whole set of them at one time. The abundance of these elements, or sorry, these isotopes is represented by the color. So the more red it is, the more of that isotope exists at a certain time. And as I play this, notice that we start with these lighter elements, things like iron, and very quickly we go up the periodic or down the periodic table, up the nuclear chart, make elements like gold and heavier. And notice that those nuclei are still unstable. So eventually, right now, they are beta decaying back to stability, and there are no more neutrons available to capture. And if any of you were noticing, the time it takes to go from iron to gold was less than a second. So this R process, this rapid neutron capture process, is named appropriately. It happens very quickly. And why I called my talk Cosmic Alchemy is because really in this R process, we can start with elements like iron and eventually make gold. We just have to make every other element in between, but that's okay. We can still make gold. So here are the isotopes in the solar system that were made by this R process. In the solar system, we observe and we find things like silver and gold and things that are called lanthanide elements. If you're not familiar with lanthanides, lanthanides go into making a lot of permanent magnets. So like the magnets that go into an electric vehicle can be made from lanthanide elements. What you might notice about this plot are these distinct peaks that are creatively named the first, second, and third R process peaks. The origin of those peaks is purely nuclear. This is a completely nuclear effect. So if we go back to the periodic table, you might remember from chemistry that the periodic table is arranged by filling the valence shell of electrons around the proton-neutron nucleus. So for example, the first shell has has a maximum occupancy of 2. The next shell has a maximum occupancy of 8, and etc. And that's why the periodic table has this somewhat strange shape. Now, the elements on the end of these rows in the last column, earn a special name in chemistry. They're called the noble gases. And why they're important in chemistry is because they are extra stable, because that valence shell of electrons, so in these plots, is completely filled. And that prevents them from reacting with other elements. They're just extra stable against reactions in chemistry. But I'm not a chemist. I'm kind of a nuclear physicist. So what does that have to do with nuclear physics? Well, in the nucleus itself, protons and neutrons also arrange themselves in energy shells that are similar to these electron orbitals. They're just not orbiting, but you can think of it as the same thing. So like the noble gases, if the neutrons and protons occur in certain numbers, then those nuclei are extra stable against beta decay. So numbers like 2 and 8 and 20, these are called magic numbers. The ones that are relevant for this R process are 50, 82, and 126. So I'm not going to ask you to remember that. But if you look on this chart here, this is again another nuclear chart. When the isotope has 50 neutrons or 82 or 126 in its nucleus, that collection of isotopes is more stable against beta decay. So those isotopes can build up during this R process. And you can kind of see, maybe you can see this pink line, it just goes vertical. It likes to stay at that neutron number. And that directly translates into the R process pattern that we observe in the solar system, because we see an extra abundance at those points. So I just thought this was interesting that these peaks occur purely from a nuclear physics reason. Okay, so back to the solar system. Again, we can find silver and gold, which are interesting elements. They're pretty. But my favorite part of this plot are actually the actinides, thorium and uranium. You might have heard of these elements because they are radioactive. So uranium can be used as a nuclear fuel source, for example. But why they are my favorite is because only the R process can make these actinides. So silver and the lanthanides and gold can also be made from this slow neutron capture process that I talked about. But the slow neutron capture process needs stable nuclei to kind of hold on to. There's no stable nuclei between here and here. So only the R process can jump that gap. And again, that's why the actinides are my favorite. So the actinides are proof that the R process has to occur naturally. We find these elements on Earth. We find thorium and uranium. But the R process or the S process, neither can occur in the solar system itself. And that means that the solar system had to have inherited these elements from somewhere else. So the fact that we have thorium and uranium means that some R process event or events occurred astrophysically before the sun was created. So in order to visualize this, say you have some star-forming gas, that gas will condense and form a new generation of stars. Those stars can evolve at different times and in different ways and eject, some of them may eject material. That material that's ejected can enrich what we call the interstellar medium, gas that is already there in the universe. And then that gas that is enriched can form a new generation of stars. So we have this cycle. And what I'm talking about with the sun and the actinides is that those actinides that we observe in the sun do not come from the sun itself. It comes from some event that happened before the sun's creation and before the Earth's creation as well. So this is one of the big questions in the field of our process nucleosynthesis. What astrophysical site produces these heavy elements? We know that an R process had to have occurred, but since the R process requires so many of these free neutrons, what in the universe can make that happen? Again, neutrons are unstable. They only live for 10 or 15 minutes, and we need a ton of them at one time. So originally, it was thought that traditional core collapse supernovae, these are the very massive stars that after they make iron, they collapse and die and have these beautiful explosions. It was thought that these could be responsible for producing all of those heavy R process elements. Modern simulations show that they could produce things like copper and perhaps silver, but probably not gold and probably not uranium either. So core collapse supernovae probably are not responsible for that entire range of heavy elements. There are other types of exotic supernovae that do occur in the universe, but there's no observational evidence that they can produce these R process elements, mostly because it's hard to observe those elements in these types of events. We have one confirmed site of R process production in the universe, and that is something called a neutron star merger. So when those massive stars go through their core collapse supernova, they can either leave behind a black hole or a neutron star. A neutron star, to first order, you can think of it as a giant ball of neutrons in space. And if you have two of those massive stars, oh, sorry, my movie just skipped a bit. If you have two of those massive stars that have evolved and leave neutron star remnants, and those neutron stars are in a binary system, then they can orbit each other. That orbit will eventually decay to a point where they get so close that they warp each other and they tidally deform each other like the moon controls our tides. It's very similar in these stars. Their gravity distorts one another. And when they do, they can eject material. So this slide just shows some snapshots from a simulation. So again, as they come together, they can tidally deform each other and throw out material. Now, neutron stars are by definition very neutron rich. So this could be a promising site of R process production in the universe in these neutron star mergers. On longer timescales, when these two neutron stars are coming together, they will eventually make one star, either a massive neutron star or a black hole. But as they are settling down, they make this accretion disk around the remnant, which can also push out very neutron-rich material. So either of these two mechanisms are one way in which neutron star mergers might be able to undergo R process nucleosynthesis. Well, like I said, there is confirmation that the R process can occur in neutron star mergers, and that's because we have a real observation of a neutron star merger. I'm excited to show you this. I hope you're excited to see it. Here it is. It is not this blob here. What you're looking for is this tiny blue glow. This is the remnant of a neutron star merger that was named GW170817. That's the name of the gravitational wave signature, and it was detected in August of 2017. So you can see in this left image the faint blue glow, and then over a few days it evolved into a faint orange glow. And this might not look as beautiful as the simulations, but this was still so exciting for the R process community, because in order to explain how that light changed from blue to red, you have to, or a lot of studies showed that R process elements are needed to explain that evolution. Specifically, the lanthanide elements, so the elements between that second and third peak. But notice that the lanthanides are not gold, they're lighter than gold. So this event, it is pretty well agreed that it made lanthanides, but there's no proof that it made gold. This didn't stop the media. You can find so many news articles that say gold was made in this event. They say that astronomers figured out where all the gold came from, and no one asked me. I disagree. And as more studies come out, it's these studies, these media studies, probably jump the gun a little bit because there was no evidence that gold was made. Gold was not actually observed in this event. Well, I don't want to be a downer, so the goal of my talk is to explain how neutron star mergers could still produce the gold that we find here on Earth. And how I approach my research is through observation and through simulation. Specifically, I look for stars that have heavy elements in them, and I also perform simulations simulations of these events like neutron star mergers in order to explain the origin of the elements in those stars. So when I say I observe stars, I actually go down and use telescopes. I've used this one here. This is the 2.5 meter DuPont telescope. And these are the twin 6.5 meter Magellan telescopes at Las Campanas Observatory in Chile. I've used this one here. I've also gone down to West Texas to McDonald Observatory and used this telescope, this 2.7 meter telescope on the right. I have not used this one on the left, but it is still an impressive instrument, and I wanted to show you. This mirror is, I don't know if you can see it, it's very hard to photograph mirrors. It's 10 meters across, and it's made of 91 individual mirror segments. So it's just a very impressive instrument. I have not had the chance to use it, though. Going to observatories is also a lot of fun. You see a lot of wildlife. So in Chile, they have their own species of mountain chinchilla. They have their own type of llama, and they have tons of wild donkeys. I'm sorry about the video quality of this, and normally I don't condone using your phone and driving, but this is a private road, so I hope you'll forgive me. Texas is kind of a different story. Instead of cute chinchillas, maybe you can read this. It says mountain lion safety and how to tell the difference between mountain lions and bobcats. So that's Texas, but it's okay because most of the time, this is my view from the control room. This is what it's like to be an observer. You have many different monitors and you're in just a room. And the type of observing I do is something called spectroscopy. If you've ever seen a rainbow, if you've ever held up a prism to the sun, then you kind of know the idea behind spectroscopy. And if you've held up that prism, you can see that the light from the sun can be dispersed into every color of the rainbow, right? Well, no, not every color. This is what we call a high resolution spectrum of the sun. This is basically a very detailed rainbow, and it's so detailed and so long, it just wraps around line to line. So you would just read this like you would a piece of paper. And what we find in this detailed rainbow of the sun is that we don't actually see every color of the rainbow. There are colors that are just missing, and that's what each of these black bands are. Each of those missing features corresponds to an element that is in the sun that is absorbing that particular wavelength of light. It's kind of blocking it from our view. So for example, this feature here is one of the most prominent features in the sun, and that's due to hydrogen, which makes sense. The sun is mostly hydrogen. So this is the type of observing I do. I take these high resolution spectra of stars and I measure all of these absorption lines to figure out which elements are in the stars and how much of those elements are in the stars. Okay, so the stars I'm particularly interested in are stars that have elements that were mainly produced by this R process. So I'm looking for stars that have heavy elements like silver and gold and platinum and uranium and thorium. The presence of this R process in these stars says that some event happened and some R process event occurred and then made the elements in them, kind of like how I argued for the sun at the beginning of the talk. When we observe stars that have this R process signature, we find that their abundances are fairly similar. So this top plot shows all of the abundance patterns of just a handful of these types of stars. The bottom plot shows the difference between them, their abundance differences. And notice that in the lanthanide elements especially, it's almost always the same pattern. And this could suggest that the R process only occurs in one place, or it could just suggest that the R process occurs similarly, behaves similarly every time. Well, there are a couple regions of significant difference. One of the greatest regions of difference is in the actinides, my favorite elements. And what my research addresses is if neutron star mergers can not only make gold, but if they could also account for these observed actinide variations as well. So in order to investigate this, I have to introduce something called neutron richness. When we talk about an R process event, how neutron rich the conditions are will pretty much determine how much of those heavy elements are produced, pretty much. So I'll show you this movie, and each of these abundance patterns is the result after I keep increasing the neutron richness. So we started out with some silver, but when I increased the neutron richness, I lost that silver, and then I started making gold and the actinides. And if my conditions are extremely neutron rich, then I really don't make silver at all. I pretty much only make gold and uranium and thorium. And why I bring this up is back to this neutron star merger event. So as I said, ejecta from a neutron star merger can primarily be ejected in two different ways, either by this wind component or by this dynamical component. And one way in which they differ is through their neutron richness. So the wind is moderately neutron rich, meaning it could produce silver, probably not gold. Maybe it could, but I'll just show you in a few slides how it could. The dynamical ejecta is theoretically extremely neutron rich. So it would be like the last part of that movie where we would produce a lot of gold and probably not a lot of silver. All right, so this plot might be a little bit complicated. Basically, it's like that movie. I'm just showing the silver, gold, and uranium abundance as I dial up that neutron richness parameter. And what we thought is, well, if we're looking for these actinide differences, we saw this waving here and said, okay, maybe that could account for the actinide differences. And this part occurs in the dynamical ejecta. This type of neutron richness is very typical of that dynamical ejecta of the neutron star merger. So we thought we figured this out and said, okay, this is how we can account for all of these actinide variations. Well, it turns out that the observations would actually point to conditions that are less neutron rich, which does not agree with the dynamical ejecta of these mergers. Okay, so if we go back to neutron star merger ejecta, we see that this wind, again, it could produce things like silver, but maybe in some cases gold if it has enough neutrons. The dynamical ejecta is kind of the opposite, where you would produce a lot of gold and actinides, but really not a lot of silver. But neutron star mergers, they should eject material in both of these ways, both with a wind and a dynamical component. So what we thought is, well, what if we just combine these? And what we found is that if you combine that wind and dynamical component in a clever way, then we can reproduce the observed abundances of stars, which are in these white points. And that the red line is that combination. Each of these blue lines is just one individual pattern, kind of like these ones. So what we found is that, yes, we do need a combination of this ejecta in an event. And with that combination, we can account for these other actinide differences. So taking that a step further, in this plot, I try to quantify how much of that dynamical component is needed as a function of increasing our process enhancement. So each of these lines, they're just different simulations. How we would read this is for stars that are less enhanced in these R process elements would only need about 10 to 20% of the ejecta from a neutron star merger to be dynamical, to be ejected in this way. And then the remaining 80 to 90% would be from that wind. Something like a normal star that's not enhanced nor deficient maybe would only require about 25% to be ejected dynamically. And then the most enhanced stars, the ones that have an abundance of these heavy elements like gold and uranium, in a merger event, they would only need 30 to 40% of that ejecta to be ejected dynamically. So what I've tried to show is that neutron star mergers through simulations can reproduce observations, especially by combining the ejecta from mergers in a clever way. They can produce stars that are enhanced with heavy elements, that are slightly deficient with heavy elements, or normal. But next, I wanted to take this a step further, and this is the topic of my current research, and ask whether we can use the abundances of stars in order to figure out which mergers made gold and uranium. So specifically, if we go back to our neutron star merger scenario, what would be the masses of those two stars in that system in order to, that would merge in order to make gold and uranium? So that might be a little complicated, but we're gonna go for it anyway. So remember that the disk wind, I said, could produce something like silver, but probably not a lot of gold. Well, it turns out that this disk wind, the amount that the merger ejects through this component, depends mostly on the total mass of the binary system. So that would be M1 plus M2. On the other hand, this dynamical component, which could be responsible for all the gold and uranium, is mostly dependent on the mass ratio between those two stars. In other words, if the stars are equal weight, then you don't have a lot of this dynamical ejecta produced. You don't have these long tidal tails. But if you increase that, that ratio so that one is a little bit heavier than the other, then you can start producing very strong tidal deformations and can produce these a lot of this dynamically ejected mass. And if we just keep increasing that ratio, we can produce more in general. It's a little bit more complicated than that, but that's the basic idea. So for stars that have these heavy R process elements, again, stars that have elements like silver and gold and even lead and thorium and uranium, I hypothesized that the lighter elements like silver are mostly set by the wind, which is determined by this mass sum, and that the heavier elements like gold and uranium are mostly set by this mass ratio, so how different those two stars are. So essentially, this is a two equation, two unknown problem where I am using the observed abundances, so even my observations of these stars, in order to solve for M1 and M2 of the neutron stars that would have merged to create all of these elements in these stars. Okay, so I'm just gonna skip ahead to my results. For stars that are very enhanced in these heavy R process elements, again, things that show a lot of gold and uranium, mergers that would produce those types of stars would have to be kind of asymmetric and in general, pretty massive. Merging systems that are a little bit more equal in mass would produce like normal stars, just not enhanced stars, stars that don't have an abundance of gold and uranium. Stars that are deficient, so they still have uranium and gold, just not as much as these like, enhanced ones, they could be produced by neutron star mergers that have equal masses. So this could be an observable difference, and this is all well and good. How does it compare to actual observations? We do have a handful of binary neutron stars in the galaxy, which are, I put them on this plot here, and these white stars. So it turns out that these stars, that these known systems are primarily symmetric, meaning like the masses are primarily equal. And compared to my results, this would suggest that present day neutron star binaries, would they merge, would likely produce lots of silver, but maybe not a lot of gold. Gold could be produced by the most asymmetric and the most massive of these neutron star mergers. So again, if that mass difference is great, then that could produce a lot of gold and uranium. So I hope that wasn't too much. And just to summarize the points of my talk, first, neutron capture, both slow and rapid, are responsible for creating the heavy elements like silver and gold. But only rapid neutron capture can create the actinides. Slow neutron capture cannot create them. The actinides purely come from rapid neutron capture. If there's one thing I want you to remember from this talk, it is that gold was not observed in this neutron star merger that happened almost 3 years ago. This doesn't mean that neutron star mergers can't produce gold. What I've investigated is the conditions under which they can produce gold. So only specific conditions, which end up being when the stars are slightly asymmetric and more massive in general. So special thanks to all of my collaborators. Again, thank you, Jonathan, for the invitation to give this talk. And thank you all for listening. I look forward to your questions.
Excellent. Thank you very much, Erika. We've actually had an abundance of questions already. So I'm just going to launch right in there. Going back to the start where you talked about the R&S process and you talked about stable elements, two kind of questions related to that. So, you've got all of these isotopes that decay to, I guess, call them stable elements. How stable is stable? Do they stay in that process forever, or do they decay eventually?
Right. So on that chart of nuclides with the black squares, most of them are stable, and if they are not stable, then they decay over billions of years. So, for example, of the stable elements, thorium and uranium, they're kind of considered stable for nuclear physics reasons, but really they are radioactive. They just have extremely long lifetimes. So thorium-232 has a lifetime of about, I think, a half-life of about 14 billion years. Uranium has a half-life of about 4 billion years. There are people who are dedicated to finding out if the proton decays, but in general, these are stable enough where they're not going anywhere between the time the sun was created and now.
Got you. So coming back as well to the R process, you had this stepping kind of laterally and upwards. It always seemed to be kind of going across to the right and up. Can you basically skip a row? So if let's say you had two neutrons that simultaneously converted to protons, effectively you just kind of skip a row in that chart.
Yeah, that's an interesting question. And there are a couple of isotopes. I'm not sure about the neutron-rich isotopes, but there are a couple of isotopes that are called like double beta emitters, where basically you have two neutrons almost simultaneously converting into protons. So that could happen. In this case, everything is decaying so quickly. Like I showed you that in the Our Process movie, the time it takes to get from iron to gold is milliseconds. So, if you're decaying twice within a picosecond, then how do you really say whether it's simultaneous or not? It just happens so quickly, it could be simultaneous. Okay. But as far as we know, all of this data, it actually relies on theory. And I'm not sure how many double beta decay nuclei we predict that far from stability.
Got you.
It's possible.
So, thinking about, stars that you look at have all of these elements because all of the spectroscopy you're doing is looking at the stars. What about planets around those stars? Will they kind of have a similar makeup of the elements that the stars have? So will they have, like, you see a lot of silver and gold, does that mean they're the places that we should go to if we want to go mining sort of precious elements? Or will those planets be completely different from the makeup that we see of the stars?
That is a question for you, actually. So, so I don't do planet formation. In principle, the gas that the planets were made out of should be made from a similar gas as the stars. So I would think that yes, if you see silver and gold in a star and that star happens to have planets around it, it should have silver and gold in the planet as well. But again, that's a question for you, since you know more about planet formation.
Just so everyone else knows, my background is I design and build instruments, but I'm specifically building them at the minute for searching for planets around other stars. So that one falls a little bit into my route, and I would agree that typically we think that the environment that the planets form from, they form from the same cloud of gas the stars form from, so we would expect them to sort of have a similar makeup. In a similar vein, and I actually don't know the answer to this one, we know the chemical makeup of the sun, and we know the kind of chemical makeup from the Earth. So are you able to say anything about the sort of progenitors, those neutron stars, that the sun and its solar system must have formed from?
That is a very difficult question to answer, because the sun is, I'm sorry, the sun is kind of a dirty star. The sun has a lot of ancestors. So I showed that cycle of star forming gas and stellar generations. We actually don't know how many stellar generations occurred before the sun. The sun has a lot in it. So if we were to know how many generations occurred before the sun, then that is a question we can attempt to answer. But one reason I look at stars is because the specific types of stars I'm looking at, they should only have a couple of ancestors. So they are more pristine, they're more pure than the sun. The sun is just kind of dirty.
Yeah, it's probably at least a third generation star, we think, so it is a bit of a mess. But
at least, yeah, we have no idea how many supernovae went into that gas in the sun. Yeah.
So let's say, looking ahead, you've said that a lot of the neutron star binaries that we see out there now, they're very symmetric, so they're not going to make gold and the uranium and those heavier elements. So does that mean, let's say in 10 billion years, assuming the universe is still around and everything else, if we're forming new stars, does that mean it's likely that effectively we'll have less actinides compared to silver and things like that in future generations of stars compared to what we see now?
That's an interesting question. I think that that depends on if there are neutron stars that are being created. And I would think that, so just to kind of give a little bit of background, the most massive stars that were created in the universe were the first generations of stars. And they would correspondingly create massive neutron stars that, like I showed, could make gold and the actinides. So it is possible that if the universe were to observe that trend where we would get fewer of these massive stars, then that would be the kind of the general way that logic would go, where in the future maybe we would just see less gold and less of these actinides. But I don't know, it's possible that we could get gold and the actinides from a different type of environment. So neutron star mergers are just one confirmed source of our process elements. Again, only confirmed in the lanthanides, not actually gold. But if the gold comes from somewhere else, like these exotic supernovae, then we could still, in the future, see more actinides being produced. So basically, I don't know. We'll see. We'll see what happens in 10 billion years.
Okay, one final question. It's kind of two questions and comments that have come in. So, you've been talking quite a lot about, how the universe creates things. What about here on Earth? Can we learn anything from, the natural processes you're seeing to make kind of new elements. So there's you see a lot of science fiction movies where they have these magical elements. One of the questions that came in was about Iron Man and Iron Man 2, where they make all of these super duper elements. Is there anything that we've kind of learned from this that you could see, practically we could put in? Maybe we don't have the technology yet to make some of this stuff. And, does anything, is there anything with the heaviest elements we've detected on Earth that would be kind of surprising to kind of some of the things that you're seeing from your research?
Yeah, well, there is one surprising thing that we found, and it's kind of the opposite of what the question is asking. So if we look at those heavy elements, those actinides, there's been some speculation that maybe there's elements much heavier than that. This would be called like an island of stability on the nuclear chart. So these extremely heavy elements, even heavier than what we have currently on the periodic table. And what part of my research has shown, this was something I did in collaboration with Matt Mumpower, Nicole Vash, Trevor Sprouse, Rebecca Sermon. This is a Notre Dame and Los Alamos group, amongst other institutions like NC State. Anyway, sorry. What we showed is that in a neutron star merger, we can't actually access that island of stability. And that's because there are these fission processes that naturally, well, or theoretically would prevent those elements from being created in nature. So neutron star mergers, they might only produce up to a point in the actinides, maybe only up to like Einsteinium, really heavy elements still, but probably not these extremely heavy elements, just because they would be blocked by fission. It doesn't mean that they don't exist. With lab techniques, we could make heavier and heavier elements. They just probably cannot be made through the R process astrophysically. So I hope that answers the question. It's kind of the opposite. We've learned that some of these elements can't be made naturally.
So we're already basically making some elements, but that can't be out there in the universe. So
well, yeah, some of these elements they're unstable, so we have really no hope of observing them.
Yeah, exactly. Well, thank you again, Erika. The recording of tonight's talk will be available on YouTube later this evening. And you can find the previous recordings of our other talks there as well. We'll be back next Tuesday, May 19th at the same time as 7 p.m. Eastern Time with a speaker from Notre Dame's College of Engineering. Professor Clive Neal studies lunar science, in particular studying the formation of lunar rocks using samples from the Apollo missions. He's the principal investigator on a proposed mission to NASA, and that is designed to study the lunar surface and its geology using a pair of landers. He's going to be joining us next week in a talk about the return of humans to the moon, the steps we need to achieve that, and how we might go about establishing a permanent human presence on the lunar surface. So hopefully you'll join us next week for that talk. In the meantime, Notre Dame is hosting its The Fight event online this evening until 10 p.m. So if you're interested in that, you can go to that, which is at go.nd.edu/thefight. In the meantime, I just want to say thank you very much to Erika again for her presentation. Thank you all very much for joining us. Stay safe out there and hopefully see you back here next week. Bye-bye for now.